Okay, so welcome everyone to this to the first Lisbon webinar in analysis and differential equations. So this is a joint event organized by myself from CAM-GSD, James Kennedy from GFM, and Nicola Van Goten from CMAF-EO. And well, there are many initiatives like this, and I think it's very healthy that mathematics continue. And now that scientific visits have stopped, we keep seeing each other and we keep sharing good mathematics. So thank you all for coming. And thank you mostly to Susanna, who is our first speaker. And I think we are starting very well, in my opinion. And as I said, if you want to ask questions, just turn on the mic and then turn it off again. So I don't know if James and Nicola want to say a few words.
Well, I don't really have anything to add to that. Ugo pretty much said it all. This is, to be fair, it was essentially his idea to begin with. So we're grateful for Ugo for putting in most of the work to organize this, and very much to Susanna for agreeing to be our guinea pig for the first talk. But yes, welcome to everyone, and we're hoping to get a good series of talks going.
Yes. Okay. Nicola, you want to say something?
Yes, I would like to say hello to everybody, every faces I know and I don't know yet. And yes, welcome to this first event on behalf of CMAF-EO Research Center. Our seminar is usually on Thursday, but now we move on Tuesday with this joint initiative, and it's a very nice initiative that I think we start today.
Okay, so as usual, I would like to present now officially Susanna Terracini. She's also a usual guest of University of Lisbon, but for the first time online. So, and she will speak about a work that, with many collaborators. I'm happy to be also in the first page. And so it's pattern formation through spatial segregation. It's also related to the title of the ERC that is now stopped. And thank you, Susanna, once again, and good talk to you.
Thank you very much, Ugo. I'm very, very happy to be the one to start this series of seminars. I am, as Ugo told, very fond of Portuguese mathematics and colleagues in Lisbon. I've been visiting MAF many times in the past, since 30 years. And I think that useful for people to stay connected, to don't feel helpless in these very difficult times, to share mathematics, but also other things related with mathematics, with teaching of mathematics, and so. So I'm very grateful to Ugo and to the other organizers for letting me share with you this talk and start this series. Okay, what I'm going to talk tonight is our various ideas and paradigms related to a research line that I've been pursuing since now it's almost 20 years, which concern the pattern formation through spatial segregation. And in general, I will spend a little time trying to explain the general philosophy of this series of papers I'm going to expose. And so the idea is that there are mechanisms that give rise to non-trivial self-organized structures. And so there is some aggregation, and this aggregation takes place because of some structures, some mathematical structures which are behind them. And so our idea is to go through a number of applications trying to catch these paradigms, which are really mathematical paradigms. In all our cases, the prevailing mechanism is interaction and will be our equation cannot be solved explicitly. There are no explicit solutions. Sometimes there are some more simple solutions. And also these problems are not small perturbation of simpler system. On the contrary, they will be large perturbations. Will be singular perturbation of systems which can be simpler or not, depending on the cases. Okay, so in general, we will face competition diffusion systems, and the formation of this pattern is driven by strongly repulsive forces, and we would like to capture the geometry and the analysis of the phase segregation, including the asymptotic aspects and the classification of the PDEs, of the solutions of the PDEs, which comes into play in these asymptotics. And these models come from population dynamics and other applications, including theoretical physics, the study of multi-component Bose-Einstein condensates, and other problems which involve, for example, optimal partitions and so on. And let's say our very basic methodology, or if you like, maybe paradigms, are rely on the following steps: the asymptotic analysis, the analysis of special self-similar simple solution or more simple solutions, the analysis of gluing technique to build a complex solutions. So the asymptotic analysis comes through the study of singular limits of systems. And what is interesting is that the effect of such singularities are common in a number of systems that come from very different applications, and include classical and quantum mechanics, other type, a number of free boundary problems, and it is related with many elements of the theory of minimal surfaces. And this means that as technical, but not so only technical tools, we see the monotonicity formulae coming into play, the blow analysis and the classification of the limiting solutions. So this is somehow a common thread between our theory and the theory of minimal surfaces. And well, there are building blocks of this type of analysis is the study of entire solutions, which appear or may appear as symmetric extremals of some energies. Symmetry and other and various type of symmetries are the key tool for the exploration of entire solution. And it's important to take into account that this entire solution may carry transitions from one configuration to another. It comes as a result of the blow-up analysis, and they are usually the limiting profile in some scaling process. Then I mentioned a big part, and a big part of this talk will be actually concerned with the analysis of interfaces. This asymptotic limiting profile have or show sharp transition of the gradients in our situation, and this may obey some reflection or refraction rule depending on the framework. And this require the study of the analysis of the interface require free boundary tools taken from the theory of free boundaries. And then I think I will not touch this, but gluing techniques involve variational method or perturbative method in various variants. Okay, so let me start with some applications, or some that you can also think of being some motivations. This plot is the plot of the densities of three populations, which are solutions of the stationary competition diffusion system. So we think that the system has already reached its equilibrium in time, and there is competition. There is here is competition. There is reaction, and there is diffusion. And what one can see here is the emergence of the interface. Here is the common plot of the density of the three population, and the blue, no one zone, so the zones where there are none of the population is present. And what we see is a nice, simple geometry of this zone. And this, please notice is the plot when the interspecific competition rates, that means that the coefficients, sorry, my video is not on.
Yes, it's on now.
It's on, oh, sorry, yeah. So please notice that the coefficient beta ij here appearing that represent the interspecific competition rate are symmetric, and this will be very important in the sequel. And the same or a similar plot arise when we have five populations, and we simultaneously plot their density on a domain. Here there is a boundary datum which is prescribed, a different one for each population. And again, here you see the appearance of regular interfaces. Regular here mean that they are regular arcs meeting at singular points with a simple rule with a definite angle, and these angles are apparently 120-degree angles. Okay, so what we have is an evolution, a system of many diffusion reaction and competition. UI is the density of the Earth population. DI that could be in general different are the diffusion rates. Beta ij are the interspecific competition rates. The internal force, the internal reactions may be different or equal, are not really, do not really play any role in what I'm going to discuss today. And also because we will actually talk of stationary solutions, so there is no evolution. Also the diffusion rates can be, to some extent, be reabsorbed in the equation and will play a little role. Here again, we are writing the system thinking that the interspecific competition rates, beta ij, are large and symmetric. In all these examples, this happens. And then we go to another motivating example, which is the example when we have coming from the theory of Bose-Einstein condensates in multiple spin states, in the case of repulsive interaction potential. So we have an energy which has an internal part and an interaction part, and for example, we seek minimals of the energy for given masses. So we have a number of wave functions which interact, and you see that the interaction is quartic, and you can think that all the other wave function stand united against the jth one. And these plot are the numerical outcome of numerical essays on this problem. And if you think the Fi are equal to 0, the internal potentials are equal to 0, and you let beta ij go to infinity, then you are actually led to the problem of minimizing the first eigenvalue of the Dirichlet form on partitions, and this is also a very nice subject which has been explored by various authors, and is very much connected with what we're going to talk. So let's, sorry for this long introduction. So we avoid the time dependency, and which in fact could be taken into account and should be taken into account, but we won't. And so we are considering this type of elliptic system. We have k component on a domain, and we may have a boundary condition. So the ingredients are diffusion, reaction, and competitive interaction. So to write this as a singular limit problem, we think that the interspecific competition rates are multiples of a given matrix. So we think that the Aij are given, beta is positive and will go to infinity. And when beta goes to infinity, we ask whether there are a priori bounds for the solution, and whether there is too many segregated limiting profiles, what is the regularity of these limiting profiles, and what is the regularity of the common nodal sets. Okay, and then maybe to understand or to put this problem in a context, let's give a look of what is called Gause's law of competitive interaction, which usually is told this way, two species competing for the same limiting resources cannot coexist as constant population values. When one of the species has even the slightest advantage over another, the one with the advantage will dominate in the long term. This leads either to the extinction of the weaker competitor or to an evolutionary or behavioral shift toward a different ecological niche. Okay, so this goes, well, this is actually a false law, and apparently Gause didn't state it. So it's a double false, but it's interesting in any case. So one point of view on this problem, which I've not touched, is whether this limiting configuration and stationary limiting configuration do exist or not. And so whether this only produce trivial solutions. Trivial means all the species are zero with one exception. And in fact, what happens is there are in fact results on this in this direction, in the direction of let's say exclusion principles, and there are celebrated papers by Mimura, which has been recently extended and developed in papers by Berstiki and Zilio, which concern the predator-prey model of two populations with a no-flux boundary condition. And in fact, what happens is that every uniformly bounded non-negative solution becomes spatially homogeneous as T goes to infinity. So actually, U and V will not segregate, but here please note that this is a predator-prey model, so the effect of the population V on the population U are the preys and V are the predators, are opposite. So we don't expect, this is not a competitive model. Competitive model will have two minus signs here. Okay, in the full competitive model, where all population are compete one against the other, then we see there are non-trivial geometries, and one example which has been investigated is a class of Dumble type domains with zero boundary condition in this case, and in fact a disconnected net of domains can be connected through thin corridors, producing cases where there is in fact coexistence even at very, very high competition rates. Okay, so let's go and let's try to be more precise in what we mean by segregation. We say that a family of solution U beta segregates. Beta, I said, is the singular perturbation parameter if they have non-trivial limits which have disjoint supported, which are disjointly supported. And if this happens again, we will ask our questions, and our questions are about the convergence, the property of the limiting profiles, and the geometry of the nodal set, where here the nodal set means set, the common nodal set of all components. And this already makes sense in one dimension, which is already significant. In this case, we have a second derivative only, and we may think of having two components, U1, U2, and in this case, let's say the geometry of the interface will be trivial in the sense that the interface will be made up of points, but in any case, this is already a type of our problems. In two dimensions, then we see the appearance of true free boundaries. In various ways. Well, first, I said we consider interaction. Let us focus on the interaction only. Actually, the reaction terms don't really play a role, but for the existence of non-trivial solution is concerned. So let's look at this term, and we start with quadratic interaction, a polynomial quadratic interaction with symmetric interactions. And then we may think, and this was the model coming from the minimization of the energies for the Bose-Einstein model. In this case, we have a square here. And this again has a variational structure, comes from a variational problem. We may think of the quadratic interaction with asymmetric competition rates, or we can think in general of changing the powers here, having P and Q different. We may have different diffusive rules, for example, fractionary Laplacians, and depending on the choice of our parameters, we will have a variational structures or not. But we can ask in okay. And then we have also an interesting related problem where the interaction between the population takes place at a certain distance. There is a fixed distance the population cannot exceed, so a fixed distance between the supports of the UI. And so in all this problem is of the particular expression of the interaction. Do all this stuff, P, Qs, Aij equal or different from Aj, and so really matter? What is there an underlying variational principle for the limiting profiles? Do the diffusion rules matter? And what is the role of distance? Okay, so let's start with a simple case, which is a variational case by definition. So we have different densities, UI. We have the sum of their internal energies. These energies are defined through some coefficients di and some potential fi. We can always think that these potentials are zero, and we just minimize this functional among all the class of segregated states. So we think that these densities are already segregated, and in this case one can prove the following theorem, which is in fact the sum of a number of results, which says that for reasonable f, think that they are zero, so you just avoid this. The minimization problem has a unique segregated stationary configuration, which is Lipschitz, and its nodal set is divided into two parts. one is relatively open in, and the other is relatively close. The relatively open, the sigma u is regular. One is made up of regular hypersurfaces of class 1 C1 alpha, and the other is small in dimension. Has a Hausdorff dimension which cannot exceed the dimension of the space minus 2. And in 2 dimensions is a locally finite set. Okay, so the picture is in fact what we have shown in the first slide. This means that there are points, actually we can say more. We can say that if in 2 dimensions, then we have a locally finite collection of curves meeting with equal angles at singular points. And in this case, we have a reflection law, which says that on the 2 parts of this partition, there are, in each part, there is only one component alive, and the gradient at the interface are equal and opposite. Okay, what is remarkable of this result is the analog with the following result on the nodal set of eigenfunctions of Schrödinger equations. That says, take a Schrödinger equation with a reasonably smooth potential, and infinity is enough, is even more than needed, and take the nodal set. And this nodal set has 2 parts, a regular part, which is in fact regular in the sense it is a collection of smooth hypersurfaces, and a singular part, which is low in dimension, and has exactly the same properties as before, but one, because here you see when you have components, you may also have an odd number of components alive at one point. In the case of one single function, you must have an even number of. Okay, and then we can consider class of functional which are connected, and in fact which are a perturbation or a family of functional which are penalized version of the J infinity. And in fact, when beta goes to infinity, it forces the components to have disjoint support. And it's relatively simple to prove that there is a convergence, for example, in the gamma convergence sense to J infinity. And what is, in fact, non-trivial is to prove that not only the minimizer, in fact, I stated for the minimizer, but all families of solution of the Euler-Lagrange equation, which are uniformly bounded in energy, then there are a priori bounds in spaces of all the continuous functions, and this gives strong convergence in such spaces. And in the case the solutions were minimizer, the limits are minimizers too. Okay, and what is something which is interesting is, and I think remarkable, is that when we have standard Laplacians, the basic rules of spatial segregation do not depend on the particular form of the interaction. Let me try to be more precise and elaborate on this point. Okay, let's go back to the quadratic interaction, the one which is not variational. As I said, this comes from the competition diffusion system with Lotka-Volterra interaction, and is not variational. So this interaction has not the form of, is not a gradient. Okay. However, one can prove very similar results that the one I stated before for the variational problem. And there are a priori bounds in spaces of Hölder continuous functions. And this means that there are limiting profiles which are continuous functions. In fact, one can prove that these limiting profiles, which are segregated, are also Lipschitz. And there are differential inequalities which are fulfilled by this limiting profile, which can be used to define a particular class of segregated states, which we call class S. And in this class, one can prove actually, one can use the notion of multiplicity of a point, and multiplicity here means the number of populations which are alive in all small neighborhoods of the point. And then we have, let's say, simple cases. There are no population alive around the point. There is only one population. There are two populations. And in this case, one realizes that there is a connection again with the zero nodal set of solution to Schrödinger type equation. And finally, with a little analysis, one understands that the real bad part of this nodal set is the part where the multiplicity of points is not 2. It's not 1 and not 2. And the set where the multiplicity is 2 is made of, let's say, is the regular part of the interface, and the rest is the singular part. And look, what happens is that if we call singular and regular parts the subsets of the nodal set I defined before, then the very same result as before, as in the variational case holds. And in fact, one can prove more. One can prove that not only this configuration has exactly the same geometric features than the other one, but it is in fact exactly the very same, okay? And so there is a uniqueness property under at least local uniqueness property. The Lotka-Volterra interaction is not variational, is not a potential. When you have be careful, this is the case with the symmetric interaction coefficients. In the symmetric interaction coefficient case, the singular limits have such do possess a variational structure, and in fact, in the limit we find exactly the same configuration. Okay, let me just make a remark here and assume that we are on the plane and we have 4 populations, and avoid just drop the reaction and try to reason this way. We have 4 populations and we alternate their signs, and we find that this object, this function, which is made by taking u1, subtracting u2, adding u3, and subtracting u4, actually is a solution. This is non-trivial, actually, of is not trivial for a reason I will say in a moment. It solves a differential PDE, and as such, if for example, if you just think of having 0 on the right hand side, is a harmonic function, and as being a harmonic function has an expansion. And in this expansion, you see that the number of nodal lines, the nodal lines are actually the 0 lines of this function. And you can see these equal angle properties because harmonic polynomials have nodal lines sharing the angle in equal parts. Okay, this is very simple. Okay, what is non-trivial here is the fact that when you alternate signs, you find a solution also through the singularity. So through the common nodal point, which is also do not need to be a point in principle. Could be a set of points. Here you need somehow a unique continuation property that should come into play. Okay, now let's go to the asymmetric case. So we take the same problem, but now we, as before, with the quadratic interactions, but now we take the matrix of interspecific coefficients, interspecific competition rates to be asymmetric. And then now instead we will find a new class of objects, a new class of differential inequalities which are solved in this case when beta goes to infinity. We always find limiting profiles, and in fact these limiting profiles can be sought by exploiting an equidarianity property. The reflection rule is changed into reflection rules through some proportionality which comes from the asymmetry of this matrix. Again, at the vanishing, all the gradient will vanish at points with higher than 2 multiplicity. But now what really changed is that when we alternate signs around a multiple junction point, then not only we have to face the fact that the number can be even, but also that the system do not close. Because each time we cross one of the nodal lines, to have a smooth gradient, which depends on the global asymmetry of the matrix. Okay, and in fact, if we try to do some numerical experiment, we see the appearance of points where the nodal line converge not with a definite tangent, but by spiraling in some way. And in fact, this can be proved as a theorem that this is in 2 dimensions. This is a general fact that the nodal lines converge to a multiple junction point by forming asymptotically some spirals. Okay, so this is, I think, an interesting fact which poses the asymmetric problem in striking contrast with the picture that we have for the symmetric interspecific competition case. Okay, even though there are still some some interesting similarities. In particular, one can prove with a lot of work that the singular points are isolated and have a finite vanishing order. The possible vanishing orders are quantized and reflect the number of populations or which are alive, and the regular part of the nodal set is smooth. Okay, let me end this talk with some, let's say, open problem. Let's go back to the parabolic problem, and and it has been noted in Inomia that spirals appear in the evolutionary problem, which are spirals, in fact, rotating spirals. Okay, and in fact, one can try to find rotating spirals and to use them or to think at them as kind of propagating fronts, okay, models for the front propagation of segregated asymmetric problem. Okay, and in fact, one can prove the existence of such spiraling limiting profiles. But this, let me show some movies about them, because there is some evidence. Okay, this is one spiraling wave in the case of three population. This doesn't move, doesn't, okay. And this maybe also doesn't move. I don't know why. Okay, let me just stop here for a moment, and then I will show. Okay, so this rotating spiral were found just by solving the parabolic problem with a logistic term and very high competition rate, asymmetric competition rate. So without imposing the rotating spiral ansatz. Spiral is probably very, very stable to appear as when solving numerically the parabolic equation. And so one can try and play games. Oh, everything is blocked, but maybe it will resume or maybe not. Okay, one can prove, for example, solving the parabolic equation with three populations, and one sees the appearance of suitable initial condition. One sees the appearance of many spirals, and these spirals are stable and stays for very long times. Okay, and produce very nice patterns like the one I'm showing to you. There should be a last one at some point with more than three components. The first two movies were showing the case of three population. If you start with more than three, let's say five population, I think this was a model with five population, then you see that things become more complex, and some components of population are not stable, but complex pattern, stable patterns, at least stable for long time, long integration times are there. Okay, I think my time is over.
Okay. I just want to, what is the initial condition? Does this happen for any initial condition?
No. No. This happened in for a symmetric initial condition.
Okay.
So where the three population actually have support which obey some symmetry condition, but the symmetry is preserved naturally along the numerical integration. It's not something which is imposed but as an ansatz or as something which is prescribed during numerical integration. So this is why I think these spirals are stable, locally stable. Okay.
So I would say that if you are done, we could try to turn on the microphone and clap. That's right.
Me? How
Everyone.
can I?
That's right.